welcome everybody to the first session of the day after the keynote. I have to say I'm very happy with the turnout. If somebody actually told me before that putting the words acid and database in a title of a talk presented as a strange loop will draw a crowd, I would actually be skeptical. And I'm extremely happy that seeing you all here. So first, just few words about myself. My name is Attila. I am currently serving as senior software engineer at Fauna, and I'm working on FaunaDB, which is our distributed and yet ACID-compliant database, which I will be talking to you about. In the past, I've been doing a lot of things. So before Fauna, I was at Oracle in the Java Lang Tools group, so I actually worked on the Java platform. I have the JDK Dynalink package in there to my name, which helps you with implementation of dynamic programming languages on the JVM. And I also did work a lot on the Nashorn, which is the JavaScript runtime that was shipping with JDK. They decided to deprecate it in the newer releases, probably because most of the team, including me, left. I feel a little bit bad about it, but you know, life goes on. And before that, I was at Twitter, where I was at the runtime systems team. I spent quite a lot of time doing JVM performance tuning and scaling distributed systems. And I, in a past life, also served as a maintainer on several open source projects. I worked on Mozilla Rhino on what is now Apache FreeMarker template engine. Apparently, everything I touch either starts out or eventually becomes either a distributed system or a language runtime. Not sure why that happens, but it seems to be a recurring theme in my career. And funnily enough, a distributed database actually happens to be both of those things at the same time. So our agenda for today, just to see approximately where do I want to take you with all of this. I want to touch on why are we even building another database. And then I want to talk about how did we implement actual strong ACID-compliant transactions in a distributed database. I will talk about our transaction log implementation, how this helps this achieving this goal. I will talk how we are balancing eventual versus strong consistency in our system. We are always strongly consistent, though. And I want to end the talk with discussing two interesting things, which is applying control theory to your distributed system to actually make it faster. It's hard enough to make correct distributed systems, and usually when you make them correct, sometimes they might have some unwanted latencies. And fortunately, there is a bunch of control theory concepts that if you rediscover, nothing is ever new, right? So these are things that were known in the 60s. And if you apply them to a software system, you can actually achieve some fun results. So to answer the question, why do we need another database? I admit I did pilfer this slide from our marketing material because I want to establish a little bit of context, but I mean, far from me to try to sell anything. I'm the worst salesperson in the world, so I'm really concentrating on the technical stuff here. So basically, relational databases are fine and an established thing where we do have transactions and they are very well understood in the business world, but then they don't allow you usually for global distribution, multi-tenancy, temporality. There's all things that we would love to have. When I say we would love to have, Fauna was actually founded by several of my ex-Twitter colleagues and then attracted a bunch of other ex-Twitter people like myself. And the 5-second elevator pitch for Fauna typically is, we're building the database we wish we had when we were at Twitter. And this includes these things. And the typical NoSQL fare also is not particularly appealing to us because they do achieve scale, but again, transactional guarantees usually fall by the wayside. And typically businesses always must make a bunch of trade-offs. So do you want data consistency? Do you want distributed scalability? Do you want development flexibility? Pick one. And so this is what we set out to do with Fauna. We try to just basically take the best of the both worlds. There's a bunch of core innovations in Fauna, and I don't want to go through all of these. These are all properties that are highly desirable in a well-designed database system. I will be touching on the right bottom corner, which is temporality, because I need to speak about that. And I will not talk about anything else except for the distributed asset transactions really here. So this is the one thing that we will focus on mostly today. So let's see what it is about. There is several ways to actually implement asset-compliant databases in a distributed system. Ours is one of them. It's not the only one, obviously. What we do, and to the best of my knowledge, we are the only company that's trying to ship an actual production-level implementation of it, is Professor Daniel Abadi and a bunch of other authors introduced a paper in SIGMOD in 2012 titled Kálmán, the Fast Distributed Transactions for Partitioned Database Systems. And my colleagues, those who originally founded Fauna, found this paper and figured that, you know what, this would be a good idea to try to build a product on that. The experiment is ongoing. So far, it seems like, you know, it's working out. It is similar in a bunch of properties to Google Spanner, and I won't really be talking about Spanner or talking about comparisons between Kálmán and Spanner. You can find me in the hallways after the talk if you want to talk about these kinds of things or anything similar. Suffice to say that Kálmán seems more palatable for us because it doesn't require custom hardware or synchronized clocks. Google is doing terrific work with Spanner, and they're also doing terrific work with providing a runtime system for it, where they have clocks synchronized to a very small known uncertainty, clock uncertainty. But they need specialized hardware for that. So what do we do here? Fauna is both horizontally scalable and it's a multi-value concurrency control store. This means two things. The database stores data in multiple replicas. Every replica contains all the data. Replicas are typically stored in different geographies, but you can have them anywhere. And within a replica, they are sharded into a number of partitions. So this here is meant to present you a single replica with 3 or 4 partitions. The temporality, which means that we are actually storing, for every row, we are storing historical values as well, actually means that you can go back in time and query the database anytime in the past. So, and you can have replicas in multiple regions. So for the sake of this explanation, let's imagine that you have 3 machines in San Francisco, 3 machines in Washington, D.C., and that's it, because normally we don't suggest you run less than 3 replicas, but that wouldn't fit on a slide, so we'll just go with 2 here. And what happens, what's interesting typically is when you are running transactions where people in different regions are trying to touch the same data. That's where it gets interesting, right? As long as they are just running completely unrelated transactions, it's not particularly interesting. So let's imagine that we have 2 customers, both want to buy widget number 3, and we have customer 2 in San Francisco and customer 6 in the Washington, D.C. replica. Both want to buy it, and we only have 1 in stock. So both of them would be running pretty much the same transaction. Make sure there's 1 in store at least. Make sure that the customer has enough store credit to buy it. Subtract 1 from the stock and subtract the price of the widget from the customer's store credit. So these are 2 transactions. Let's presume that they're running at approximately the same time in both places. So we have the San Francisco replica, we have the Washington, D.C. replica. One client connects to the San Francisco replica, tries to run this transaction. Another connects to Washington, D.C. replica and tries to run this transaction. What happens? At first, the node that, let me just go back one slide. So the node in each replica in the upper right corner, we will presume that that node is our query coordinator. It runs the transaction. So what it does, it reads those rows for both the customer and the widget. It will probably need to fetch them from some other nodes in the replica because we try to do, well, we're doing more or less random partitioning right now, so data is just scattered in the replica, so it will pull the data from other nodes in the local replica. The node in Washington will do the same, except it will be doing it for another customer. And then it will calculate the set of writes. So what you have there is that the numbers in red say, okay, so I checked the stock, the customer can buy the widget, I need to write a new value for the store credit, and I need to write a new value for in stock, which is 0. The same thing happens in Washington, D.C. The customer there has a lot more money, so instead of 21 for him, we write back 421 when he wants to buy the thing. And what we do now is we submit, so both replicas will be submitting these transactions to a transaction log. Transaction log is defined by a consensus protocol. We do use a interestingly modified version of Raft. We do have an interestingly modified version of everything, really. And these transactions will get into the log. The log will guarantee unordering. It is not guaranteed. There's no guarantee really which one of those transactions will get committed to the log first. It's one of those, dirty little secrets of distributed systems, basically, that as long as you did not act back to the client, you can reorder all you want, right? So you can just claim that the order was whatever. So one of those will get into the transaction log first, and the other will get in the transaction log second. What we also ship with the transactions is the timestamps and the keys that were read. We are not taking any locks when the transactions are run. Rather, we are using, instead of pessimistic locking, we are using optimistic locking. So as part of the bundle that goes into T10 and T11, so the data that comprises the transaction is both the write effects of the transaction and also the read keys and the read timestamps. The slides here are written as if we are sending the values that were read, but we are actually sending over the timestamps. It's just as good. It's actually better. And eventually, the nodes that store data in every replica will be reading the log, and they get to T10. And both the San Francisco replica and the Washington replica will read the transaction. And they need to rerun the reads at the transaction's new time. So they need to rerun the reads at T10 and see whether they still match what the reads that were in transaction. This is the optimistic concurrency. This is part of the optimistic concurrency control. And if the reads happen to be the same, we just write the new value to the underlying data store with the timestamp of T10. What you can see here is that both replicas, even though they're geographically separated, will arrive at the same decision. They will deterministically read the same data because all the replicas contain the same data. We start from the assumption that all the replicas contain the same data. So when they rerun the reads locally, they will see that nothing has come in between T10 and when it was run and modified any of the rows. So it's safe to apply the write effects of this transaction to the underlying storage. I'm not saying commit because technically commit already happened when the transaction was made durable in the log. You can't lose it then anymore. So we call this phase apply. And now, The next transaction, T11, comes along, and both replicas are running it, and they are reading, and they do the same thing. They need to reread the data at timestamp 11. And what they will notice is that there is a difference, because in the case of T11, the row for the stock, the row for the widget and the value for the stock in there already has a new timestamp, T10, and it was read at T7. So it means that the transaction 11 lost to transaction 10 on the optimistic concurrency check. So it needs to abort. And it can deterministically abort both in San Francisco and Washington, D.C. So this transaction at this point is aborted. What is important to see here, and what is actually a pretty nifty property of this, is that all the cross-system coordination only happens with achieving a consensus on the log itself. After we achieve the consensus on the log, the nodes that are applying the transactions are reading the log. So even if they fail, even if they're shut down, even if they lose availability and come back later, they have their own persisted, well-known index. They just start reading the log from there, reapplying, and they eventually catch up. And all will catch up in the same deterministic manner. Of course, there's no silver bullets and there's no free lunch. There is obviously an additional element here, additional computation really, which is that when the nodes in a particular replica are applying a transaction, they need to redo all the reads. And some of those reads will be remote. And if the transaction's write effects actually affect several nodes, then all of them will need to ask for the reads from each other. So there is definitely a bit of an additional quadratic component to the thing that we typically try to mitigate by eagerly reading and broadcasting within a replica. So when a node is applying a transaction for which it does have write effects, it will have to read its own storage for its local subset of reads that it needs to perform for the optimistic concurrency check, and then it will send them to other nodes in the replica that are affected, and other nodes will receive those, cache them if needed, and then when they are applying the transaction, they will actually consult their own cache first. So, this is hardly groundbreaking, but it's just one of those things where we are trying to optimize something and minimize the amount of work that needs to be redone. This protocol actually, and as I said, we have an interestingly modified versions of all the protocols that we use. This is not vanilla Calvin. Vanilla Calvin, as described in the paper, does not run the transactions on a coordinator. So what we do, we run the transaction on one node, we compute the write effects, we gather the reads, and send those to other nodes, which will then redo the reads. Vanilla Calvin actually requires you to encapsulate the logic of your transaction in the transaction itself. So in transaction, you're basically like shipping little programs that need to rerun deterministically on all nodes. And that obviously also has to mean that those little programs can deterministically get rerun on every node. So they better not try to get the current system time, invoke a random function, do a file IO or anything. Not like we are actually doing any of that, but it would be, in most cases, it would be computationally even more expensive because you would need to rerun the whole logic of the transaction on every node. So as I said, we don't need clocks, we don't really need locks. Well, optimistic concurrency control is kind of a locking, except different. But we don't have to rerun the transactions on every node as such, but we still need to do the rereading the timestamps for concurrency control. So how are we doing the transaction log? Because so in the previous slides, I just told you that, we have a transaction, we toss it in the transaction log, it gets read and it gets applied. Well, okay. And so far, it's a hand wave. I just hand waved it away that, yay, we have a consensus-based transaction log. How does it look like? So in order to have ACID transactions, our transaction log is helping a lot with it. We can guarantee that the transaction is always entirely written to the log, and that helps atomicity. It's not the whole story of atomicity, but it definitely helps. The log will order transactions, which helps both with consistency and isolation. And finally, once written to the log, the system can't lose transactions, so they are durable. Well, can't lose transactions until you lose more than a quorum of the nodes, but that's like the standard asterisk disclaimer for all the consensus-based systems. What we typically say is like, well, run a lot of nodes. It's funny because you can get FaunaDB Developer Edition, which lets you run it on a single node, so on your laptop really, but it's not terribly redundant, you could say, but or you really need, can use that forest to experiment with it. Right, and then the data nodes will eventually be reading those, will be pulling data from the log. Well, the log nodes are eagerly sending transactions to data nodes if they know that they are basically on the front of applying them, and if nodes fall behind, they can pull. So there's in a lot of parts of the system, we have dually both push and pull mechanisms to ensure that the system just keeps pumping. So where is the log? Obviously, it's not in any one place. It is a distributed thing. The log is based on distributed consensus. As I said, we're using Raft. We could be using Paxos as well. It wouldn't be making any particular meaningful difference, I think, at least in terms of capabilities. And for log, multiple machines will work together to agree on what is in the log. Typically what we do is we scatter log nodes across replicas, so why put all your eggs in a single basket, right? So instead of having all the log nodes being in a single replica, we prefer to have one log node in every replica. We have more of them, but for the sake of the simplicity, let's roll with one right now. So what happens is that clients connect, and I have not pictured the clients here, so the little green dots are the transactions, and the white circles would be nodes that can act as query coordinators. Clients connect to them, they run transactions, they prepare the batch, which is the transaction, which is the read effects and write effects, as I said, and they send them into the transaction log. Obviously, node can serve multiple purposes, so it can be a coordinator and a data node and the log node at the same time. So some of those can even be sending transactions to themselves, which actually is pretty cheap. They typically, if a node is both a log node and a data node, it will obviously prioritize sending to itself because spare a network hop. And then those transactions end up in they first end up in the memory of the log node. At this point, they could even be lost if the node just crashes at this time, but then the coordinator is also still keeping it, so it would try to send it somewhere else. Calvin protocol works in epochs. We chose an epoch to be 10 milliseconds. So what happens is that the log nodes will be gathering transactions in memory until 10 milliseconds pass. And then they will gather all the transactions they have in memory for those 10 milliseconds and then write that as a single message. That they will write this batch as a single message in the transaction log. Multiple nodes can write a batch for the same epoch, so there's no one-to-one correspondence between an epoch and a message in the log, because if all three of those nodes that are in the log have gathered some transactions in memory, they will all produce a message. And now the green dots are our current epoch, and the otherwise colored dots are meant to demonstrate transactions from a previous epoch that are already committed to the log. So they write them to the batch, and when we say write them to the log, this really means that the messages are being proposed into the draft consensus system, and eventually, when enough of them agree that the message should be appended, then it's considered committed. Every log node will store a copy of the resulting log, which is good because then the data nodes that use the log, they can just read it locally, and they can apply the transactions to their data storage. The system has both, as I say, it has both pull and push systems. Having a single node log would be a performance bottleneck. In reality, we always recruit more nodes to be log nodes, and they will form multiple raft rings. So they will form multiple logs. At this point, we typically switch terminology and say that we call each of those rings is a log segment, and when they are taken together, they are the entirety of the log, which actually leaves you with a bit of a problem, because now you need to merge these deterministically. So Kálmán is all about determinism. And what we do is each data node now, when it wants to apply transactions for a particular epoch, it needs to fetch them from all the log segments and then deterministically merge them. When I say deterministically merge them, there's several strategies to do that. We are not doing anything fancy. We basically just number the segments and say all transactions in segment 1 for a particular epoch come first, and then all the ones for segment 2, and all the ones for segment 3, and so on. We could be doing something more fancy. We could be playing with the modulo and permutations based on the epoch number to make it more fair. Right now, we don't. A friend I have who works in fintech industry, when I was explaining this to him, he was immediately like, ooh, my clients would definitely be figuring out how to always submit into the log segment 1. Just like get that edge to my transactions will be the first in every epoch. I mean, I can understand the sentiment. Okay, so nice thing about the protocol is that it does not actually rely on clocks for correctness. The epoch's timestamps are logical. In practice, we do use, on our own deployment, we do use NTP, and God so help me, I had to write an internal sync protocol, which, I mean, I would never claim that anything like this is correct, but again, fortunately, we don't need clocks for correctness. We just need to ensure that the epochs in different log segments roughly keep to each other, and if possible, also hew to the real time. So these are nice properties to have. Even if you don't that, at worst, what it causes is that if any log segment is in the future, then any transactions that are committed into it will have to wait until other log segments catch up so that data nodes can then deterministically merge that particular thing. And I think in a system we run typically with a 30-second write timeout for transactions. So if it's skewed more than 30 seconds in the future compared to everything else, then those transactions that log segment will just be experiencing timeouts, which hopefully somebody monitoring the system would notice. But again, this might affect availability in this sense. It does not affect correctness. You can't ever corrupt the data that way, though. So this is the log, as I said. And let's see, eventual versus strong consistency. We have a moment in the protocol when the transaction we know that is durably persisted, so its effect will eventually become visible, but we don't know what's its timestamp yet, because remember, we need to actually merge all the transactions from different segments, and it's the data nodes, when they merged everything and when they apply, they all independently but deterministically arrive at the same timestamp for a particular transaction. So the time diagram looks something like this. So the client submits the transaction to the coordinator submits it to the log. The log, after the raft has reached the consensus that, yay, we committed it, it will actually act back. If its in-memory buffer is full, it can reject it, and coordinator can retry a different one. And at this point, when it got back a commit message, it could even act back to the client. That's the first dotted line. We don't do that. It could only act to the client saying, hey, your transaction is durable, it will eventually get applied. And then you would get a system with eventual consistency. We chose not to do that. Eventually, the transaction we get from log node to the data nodes, there's the little OCC check arrow there as well. And the data nodes will all achieve the same outcome, which is either I applied the transaction and this is its timestamp, or I had to abort the transaction because it failed the OCC checks. At which point, this information again goes back to the coordinator. The client is still waiting. We still haven't acted to the client. At this point, we could act to the client. We have a timestamp or a rejection message, but let's presume we have a timestamp, right? So it's successfully committed. And at this point, we could act back to the client, but maybe not all the nodes have already committed their parts of the transaction. So the first node that reports back the timestamp, we could already use that to act back to the client. But if they try to read back now, they might be blocked. And turns out, psychologically, people don't like when the reads are slower. So, we just decided to do a bit of a wait until the local read clock on the coordinator catches up. That's an interesting question, actually. Like, how do you figure out how much to delay the read clock? And this is only the time when we act back the transaction with the timestamp, and the client retries, does a read, does another transaction saying the snapshot time is now the timestamp that I got from the previous one. He will be guaranteed to observe all the effects. So, as for the transaction language itself, we do not have session transactions. Our model currently doesn't support them. So basically, you don't issue, like with SQL, you don't do begin transaction and then through a JDBC driver, you issue an update and a select and a delete and whatever. But rather, and then at the end you do a commit. But rather what we do is the whole logic of the transaction must be sent from the client as a single request. So very similar to how SQL stored procedures would work. Originally, Kálmán had this limitation because it required all the transactions to actually execute on all the nodes. We don't have it as we actually run the transactions on just a single coordinator. So we could be keeping a session there, right? So for multiple client-server request round trips. We didn't implement it because the language itself our query language is actually very expressive. So this is taken from an e-commerce tutorial that we have on our site. And as you can see, it's very Lispy. If you're into Lisp, you will like it. If you're not into Lisp, then these days we also have a GraphQL adapter for our system. So you don't have to like Lisp. But for better or worse, our language is very Lispy. And this is hypothetically how it would work, right? So the client could be doing multiple round trips similar to like select and update and delete and whatever. And then when it issues a commit, that's when the coordinator would be sending to the log, and from there on it all works the same as in the previous example, and we would eventually, well, the only difference is that when the client in this case would say commit, they might get back an exception saying that your transaction was aborted, sorry, because you lost the optimistic concurrency check. This is something we could do, but as I said, people seem to be happy with the lack of session transactions so far. I'm not saying it will always be the case. We could probably implement this when we wanted to. But it's an interesting thing that with this modification of Kálmán, we actually have the ability to have session transactions. Technologically, it opened the way for us to have them. All right, so for the end of the talk, I want to talk about a little bit about like control theory aspects that we put into the database. Actually, we talked about two. One we put in and the other we plan to put in. So that one is only speculative, but it's a fun idea. So the idea with control theory is, let's presume you have something that works correctly. It's, as I say, it's hard enough as it is to write a correctly operating distributed system, and make it somewhat faster. So typically, coordination bottlenecks, latencies, and so on come in, and we can use things. So one thing that we do use in Fauna is a PID controller. It comes from proportional integral derivative. It's a funny little feedback loop for continuously modulated control. Probably everybody has encountered it because the cruise controls in the car are an example of a PID controller. What it does is you always have a set point, right? So, and it's a car analogy. Of course it's a car analogy. You can't escape a car analogy. Typically, with a cruise control, you have a set point, which is the target speed that you want to go. And you have a current process variable, which is the speed at which you are going. difference between two is an error value that you want to compensate. And the system, the controller, is doing it by exerting a modification to some control. In this case, in the case of the car, it's the throttle. However, the system doesn't know on its own, it doesn't have a model of how changing the control, the throttle, will change the speed of your car, right? So motors don't change torque instantly. If you're going uphill, if you're going downhill, then the coefficient of the throttle to the change in speed will change. And obviously, if you're going faster, then you need more throttle to also compensate for the wind resistance, yada, yada. So it needs to be continuously modulating the system. What the desired properties of it are that you want minimal delay and you want minimal overshoot, because in that case, you will end up with oscillations. So the way it works, and I'm really sorry for throwing a mathematic formula at you, is it's taking a weighted average, really, of the integral of previous errors, that's the I, and the derivative of the current error, and the actual proportional difference in the error. And how do you weight these three? Because the K coefficients there are actually the weights between the proportional part and the integrative part and the derivative part, which will give the characteristic for the PID controller. And it's a bit of an art to tune the weights to make sure that it converges rather than overshoots. There is a fun little demo for this, which obviously features a car that you can see. So here well, if it works, it is notoriously fuzzy because I didn't write this. And right now you see it working, and then if I move the car to a new position, you can see how the controller is actually compensating for it. And then quite often, you can also tilt the terrain. And then here you can actually play with like what happens if you can play with like canceling out the proportion or the integrative or the derivative, leaving only just that, and see how does it affect, whether it will quickly compensate nicely, whether it will overshooting, whether it just asymptotically struggle to reach the value but never actually reach it, and so on. So, okay, so that's cars, right? But what does it have to do with distributed systems? What we use it is to control when to issue backup reads. The backup reads are when there's a node, it needs to read a value, the value is not on its node, it's on a different node, and it needs to read it from the other node. It presumes that the other node is actually alive. We have a separate fire accrual detector to detect nodes that are down. So normally the one that's local, in its local replica, will be the one that it first targets. But if it doesn't respond within some time, then it will also need to issue a backup read to a node in a different replica in an attempt to actually obtain the value that it needs to read. And the question typically is when to issue the backup read. There are two extreme strategies. The one strategy is, well, issue a backup read immediately. Always do 2 reads. I mean, why not? You can do it, except you end up with double the traffic on the network. The other extreme is, well, never issue a backup read. So if the first node that you attempted doesn't work, time out to the client, let them retry. Not the best user experience, but it might also work. However, if you do have a PID controller in there, then what it does is it can actually controlling this delta t. So the control here is the time to issue the backup read. So it issues the first read, and if it doesn't answer within the delta t, then it will issue the backup read to some other node. The process variable that we use is the proportion of reads that timed out recently, which you actually can go down and set it to 0, or you can set it to some ridiculously low value that you want it to be effectively 0, like 1 in every 10,000 or so. If you set it to 0, though, then it can't really ease back on its own. So with PID driving the time to issue the backup reads, the nodes will basically automatically tune when to issue them. When everything is humming along, then the PID controller will just be increasing the time until it increases it past the timeout, so they're never issued. If parts of the system start acting erratically, things are down, then it will start shortening the time to issue the backup reads, and it can pull it back all the way to 0, which basically means issue the backup read immediately with the first read. So that's what we are using it for. I was also gonna talk to you about the Kálmán filter, but I think we're actually at time, I believe. Well, you know what? Are we? Yeah, it's time. Okay, it will be in the slides. The fun thing about the Kálmán filter is we don't use it yet in Fauna, but we are planning to use it, and it's also another little thing that in practice, typically what you see it in is in GPS systems. So when your phone typically tells you like, hey, you're here. Oh, you know what? You're actually here, and it pulls the little blue dot to somewhere more precise. So that's basically a Kálmán filter at work. It's taking data from multiple sensors, accounts for noise, builds a bit of a, probability model, and then based on that, it can achieve a better value than what you would have if you only had one of those sensors or the sensors just read separately. And we also have a use for that in a distributed system to speed things up. Unfortunately, I don't have time for that, so it will be in the slides though. All right, so in summary, we can create database systems that are both distributed and ASIC compliant. We use the Calvin protocol for that, and Raft. We have a modification of the Calvin that preserves its desired properties. We don't rely on locking or clocks, which is great, and control theory can speed up your stuff. Thank you for your attention.